we're going to go to that. Right before the example, there's the bearing stuff, or there's the different ways of measuring angles right here. All right. So we have to learn how to say these different angles. They show us in this textbook one way to describe angles. So west 30 degrees south, west 40 degrees north. So if someone tells you that as a direction, what they mean is start at west. If I started at west and then I went 30 degrees towards the south, does the diagram make sense? Okay? Here on this one, if I started at west and went 40 degrees to the north, that would be the direction. Now, depending on which textbook, there are other ways that angles are stated. This angle sometimes is stated like this: 30 degrees south of west. Can you see that that means the same thing, English language? You look at it, it's 30 degrees south of west. That means start at west and go 30 degrees south. I like the first one that we've highlighted a little bit better because it's very direct. Start at west, 30 degrees, then south. Right? How would I say this one in this kind of language? 40 degrees north of west. Have you ever heard in a movie where they've got like a ship going through the sea and they say you need to get your bearings straight? Or have you ever heard that expression with bearings? Okay. Bearings is another way of measuring direction. And the way that bearings work is it's kind of like a standard angle, but instead of starting at the positive x-axis, bearings always start at north. And we say north is 0 degrees. And so this 30 degrees that is south of west, or west 30 degrees south, if we started at 0 north and went around to here, what angle would that be? It would be 180 plus another 60, so it would have the bearing for that angle would be 240 degrees. So there's another way of saying that same angle. This angle in standard position would be 180 plus 30, which would be 210 degrees. So we have a number of ways of saying the same angle. What would the bearing be for this one? Oops, all the way up to there. 310 degrees. So if you had a bearing of 310 degrees, so depending on the question, you have to be prepared. You know, if the language is this way, or this way, any of those three, you have to know what they're talking about to get the angle correct to start with. So now we're going to go till you get to the end. And basically, you know that this is 90, this is 180, this makes 270, plus 40 more gives me 310. Because you just count by 90s. 360 minus the 50 that's left, and get 310 that way too. Perfect. Now in our first example, here we've got east 40 degrees north. So we got to draw where that would be. North, south, east, west. Did you have trouble remembering that as a child? No? Do you have crazy things to help you remember this? Okay, yes, I've heard that one before. Never eat soggy wieners. How many people have heard that one? Okay, that's how you learned it. Never eat soggy Oreos in French. Can you say it? How does it go in French?
Well, no, you say it in English, but like.
You say it in English?
Oh.
Oh, because it's an oh. Is there anything in Spanish that you had to? No? You just, Spanish people just know this stuff. It's common sense. Okay. Some people say we. They remember north and south, but they can't remember east and west, so they just say, oh, that spells the word we. Anyways, never eat soggy wieners is way more fun. So we've got east, so we're going to start at east, go 40 degrees north. That would be this angle right there. East, 40 degrees north. And there is a fire. We get to draw a fire. It is a good day with some smoke. Right? Little person screaming. Ah! Oh, I didn't want to do that. No, it's not in the air. We have to remember, this is not in the air. This is, you are looking from above down, right? Because north is not up in the sky and south in the ground, right? That would be confusing. So this is from, so now this is looking from top view down. There's our little fire. There's our little guy that's screaming, calling for help. And there's a forest ranger who hears that person 30 kilometers away yelling. Very quite likely, right? They hear someone yell for help, then they see the smoke, and they say, oh, that looks like 30 kilometers away, because they're really good at that. But in order to get there, they have to travel east and then north, so what we need to do is draw our triangle. There's our triangle. We need to figure out how far we need to go in our x direction, how far to go in our y direction, and we can use trig to figure that out. Here's our trig ratios and help us remember which ones are which. Which one do you want to find first, x or y, or do you have to find one before the other one? It doesn't matter. So if we want to find x first, if we want to find x, what do we know? We know the hypotenuse and we know an angle. Now, with that angle, what is x? Is x the opposite, the adjacent, or the hypotenuse? It's the opposite. And we know the hypotenuse. So when we go through our ratios, we know that we're going to have to use sine to find x. So we can write it out. Sine of the angle of 40 degrees. No, sorry. Cos. My goodness. We know we have to use cos because x is the adjacent side to the 40 degrees. There we go. Yeah, no, I'm just going crazy. So here we go, cos of 40 degrees. The adjacent side is x. The hypotenuse is 30. And now you just have to use your algebra to solve for x. How would you get x by itself? Times both sides by 30. And you get 30 cos 40. Type that into your calculator. Make sure your calculator is in degree mode to get 22.9 to the nearest kilometer would be 23 kilometers. Now if we want to find y, now we can use sine because y is the opposite side. Multiply both sides by 30. .28 to the nearest kilometer would be 19 kilometers. What's that? Who came up with trig? Well, what happened is people noticed that if I took different triangles, okay? Who came up with trig? Let's take one of the favorite ones. If I take 3, 4, and 5, need to go back quick. Good. Oh, this isn't drawn to scale. This looks 19, yeah. I'll make the 3, 4, 5 this way. What they noticed is this happens to be about 37 degrees, okay? What they noticed is if they made any 37-degree triangle, okay? And they went and they measured this side and it happened to be 6, this side happened to be 10. They did another 37-degree triangle and they noticed that this side happened to be 9 and this side happened to be 15. And no matter what triangle they drew, this fraction, 3, right? Opposite over hypotenuse here is 3 over 5. Opposite over hypotenuse here is 6 over 10. Opposite over hypotenuse here is 9 over 15. Well, you knew you could reduce these fractions, and the fractions always reduced to be the same thing. So then they said, well, if I know this is 37 degrees, and this is, you know, I'll pick a number that works out nice, 21. Because I know what the ratio should be, that sine of 37 degrees is always 0.6, they started to say, well, sine of 37 is 21 over x. And I know from experience that this is 3/5. And then you have to say, well, what would x be? And then the only way that this works is if x is 35. And sure enough, if you would go to your calculator and actually, let's actually do the math here. You times both sides by x, then divide by sine of 37. Now I've rounded 37. It's not going to be perfectly right. It should come out close because I think the actual angle is like 36.9 or something. But if we go to our calculator and type that in, 21 divided by sine of 37, because the calculator has memorized what 37 opposite over hypotenuse is. They have every single angle imaginable built into your calculator. And sure enough, 34.89, it tells us, yes, it's very close to 35. And that's how trig got invented. It's not necessarily something that just someone made up. It was a pattern they recognized that no matter how big or how small the triangles are, those ratios stay the same. You could solve everything. They were doing trig stuff already. The Greeks were doing trig stuff, 500 BC, 300 BC. They noticed this pattern, then it's just a matter of defining it, okay? And the way they initially got all the ratios is they were just very meticulous in measuring. If someone measures 37 degrees perfectly and then measures the opposite side and the hypotenuse perfectly, then they get a ratio. Then they write that ratio down, and now they can use that to figure out other stuff. In fact, when your parents went to school or your grandparents went to school, we used to have tables. Let's see if I've got, yeah, here, I've got one here. Because we didn't have calculators when we were so old, you would get tables of all those numbers someone had figured out, written them down, and you'd open up your book. Because you don't have a calculator, you'd open up your book, you would find sines, you'd find the angle. So what angle did I just do? 37 degrees. Here's 37 degrees, and it says decimal 60181. We were using 3/5, which is 0.6. So our numbers are a little bit off. This is more, more accurate. And you have a whole bunch of different angles. Now that we have calculators, these tables, this breaks up things to decimal places. It has 60, and then it has 60 and 6/60ths, 12/60ths, 18/60ths.
People cheat on these?
Multiplying with lines work?
Yeah, like you know the things people learn how to multiply, like draw crosshatch lines.
Yeah.
How does that work?
All right. Well, I'll show you that too here. I'll just change. That's the last thing with